Have you ever wondered why certain systems are faster to respond, certain not very fast to respond? For example, I come into my home on a hot day where the outside is 40 or 45 degrees. I come home, I switch on the AC, and I want the AC air conditioner to set the room temperature to 24 or 21 to cool me down or cool the room down immediately. It takes its own time, no matter whatever your set point is. It you put it at 16, 21, or 24. There is some time for the AC to cool down from 40 degrees to a 21 degrees or a 24 degrees. Same thing on a winter morning, you want to take a hot bath, you switch on your geyser. It takes some time for the water to heat up. What goes into these, or how do we understand such behavior? Or why does it take time for the water to heat up or for the air conditioner to cool down the room? Hello and welcome to this lecture number 1 of week 4 of the course on control engineering. The title of today's topic is time domain analysis, and we will in this focus on how systems respond to different input or test or reference signals, and specifically why does it take so much time for the water to heat up or the room to cool down. So how do we therefore understand the performance for any input signal? If I know how the system performs or reacts to a certain input signal, it will help me in my desired control problem. It will help me to design a control system which meets the desired response of control requirements. Requirements could be to go to set the room temperature to 24 degrees or the water to 60 or 70 degrees, and how fast or how slow. One is a specification of the desired steady state, if I may call, and also is a transient behavior of how fast I want my temperature of the water to rise or the temperature of the room to cool down. So this in this context, we will call this as the time domain analysis. It largely refers to the analysis of a system performance in time, right? How does the temperature evolve of the water or of the room with specifically with respect to time? So there are two common ways of analyzing response of systems. One is the natural response, and second is the forced response. I'll see it. We'll do a little examples on this, but it is easier to visualize what is the natural response. Natural response would be, say, if I take my fan and maybe I just perturb it with my hand. I don't really apply a voltage signal, but I set it at some certain speed. The natural response, the fan will just rotate and again come back to its zero speed. Forced response is when I switch the fan on, it goes to a certain speed depending on which position my regulator is 1, 2, 3, 4, 5, and so on. So there are two things here. One is that in addition to natural and forced, we also have the transient and the steady state response. The transient response would be all the response my fan or all the time my fan takes from the zero speed to reach to its desired or the set speed. And the steady state would be once it has reached its full speed, it just continues to be there. Another way to look at natural or forced response is I wake up at 6 a.m. or 5 a.m. And the natural response would again be, maybe I set an alarm to be a little ambitious, to wake up early in the morning. The natural response would be to shut the alarm and go back to sleep. Forced response would be, oh, I have a class at 8 a.m. I have an exam at 8 a.m. or I have to catch a train, take a flight. That is my forced response. Here, the transient response would mean how fast maybe I get ready to show up in my classroom. And steady state response, once I go back to the class, I go to the class, I wake up, I go to the class, and once I'm in the class, I may sleep there. That is my steady state response. Loosely speaking, how do we understand this? So in both of these cases, to understand the complete response of a system, I need to know what is its natural response and also the forced response. Right? So what happens without any input signal with some initial condition, and what happens to the system with some input signal. and also how fast the system moves or how slow the system moves, and what happens in the steady state, what happens eventually in the system. So let us start with some examples which we are now familiar with. So by now I'm assuming we know how to visualize a behavior of circuits. So if I just take a simple RL circuit, which is, and we have done this extensively also in this course, so I will have, well, given for a certain given L, certain resistance, this is my equation, right? And there is no input. Okay, so so this is the solution of the differential equation. If my initial current through the inductor is 5 ohms, what I see is that the current starts with an initial value of 5 and goes till here. It just goes back to 0, which means there is some energy stored in the inductor initially, and with time the energy is dissipated through the resistor and the current comes to 0. Just like a fan at some initial speed without the input voltage has some initial inertia or initial energy that gets dissipated via friction in those mechanical components, and the fan loses all its energy and comes to its zero speed. Interesting would be what happens when the initial current I0 is itself 0. Okay, think of this, very simple answer. And now we were interested also in the transient versus steady state. Steady state, yeah, I can just look at my fan, it's just the zero speed, or in this case, the zero current. What happens in the transient is from this current of 5 till reaching the current of 0, it happens roughly around this time, right, when it's almost like 0. So this is the transient. Okay, transient is also, you look at a fan at its full speed. I switch off, I put off the switch, which means there is no voltage source. The fan has some speed and it slowly rotates and comes back to a zero speed. So the process from when I switch off the fan till it reaches the zero speed is a transient, and after it reaches the zero speed is the steady state. And it also depends on if the fan is at initial speed of 0, it continues to be 0. There is no transience. It's always in steady state. Force response, things would get interesting if I just put a voltage source here. Then I have, okay, instead of L di by dt plus Ri being 0, I have an input voltage, which gives me a solution to the differential equation of this form. I can do it in the Laplace domain, the inverse Laplace, and so on. It will still lead me to this same behavior. Okay. Now, what am I trying to do here? I'm trying to look at systems response with some initial conditions, systems response with a step, and in general, to see how a system behaves, I would give it certain test signals, right? So if I do not know how the system in general behaves, so I will just give some test inputs to see how my system behaves, in how the system evolves or responds to these test signals. To analyze a performance, therefore, the system is subject to standard test signals. So in general, control system design specifications are based on response to such test signals. And here my standard test signals would include a unit impulse or just an impulse, with which essentially means that physically I'm just looking at how the system responds to any non-zero initial conditions without any input. As a simple example, it just here I'm just looking at a non-zero initial condition and no input. So I just call this as the impulse response or the natural response. Then I see how the system behaves to a sudden change in input. Right, my fan is at zero voltage. I switch on, it immediately experiences a voltage of 230 volts. Then what happens? And similarly, I can have test signals. So I had the impulse of this form. Then I have a step of this form. Signals could be of ramp, a parabolic nature, and so on and so forth. And this behavior, or understanding the behavior of the system to such inputs, will in general give me information of system to any kind of inputs, because they would, these are signals in real time would be combinations of these signals or some kind of variations of these signals. So we will largely concentrate on system response to standard test signals. Okay, so let me start with a first order system in closed loop. So one of the formula that we will use here is the closed loop system. So I have a plant. If I have a reference here, something here as the H, and so on. So this is my Y. Here C equal to 1. The closed loop H is also equal to 1, right? So the closed loop transfer function from Y to R will only be P over 1 plus PC. Okay, which will just mean that this is 1 over tau s plus 1. So tau is a constant sitting here. S is usually the Laplace or the S domain that we are working with. This tau is called the system time constant. This number tau determines how fast or how slow my system responds to an input. We'll see this mathematically. That is, higher the time constant, slower will be the response, and vice versa. Okay, we'll just ask math of how do we justify this. Okay, so let's take a couple of cases here. Say I buy a very fancy car. One of the selling points is how fast my car goes from a speed of 0 to 100. If I just model my car in this way with a tau of 0.5, set my reference to 100. Okay, step input, I also call this a step reference instead of just an input. So the system is set to a reference speed or desired speed of 100. I just check what is the y of s for this step of size 100. Okay, I just do the inverse Laplace transform and I get something like this. If I just plot it, I just get that, okay, I start from at t equal to 0, I'm at speed 0. By the time I reach 3 seconds, I'm already at 100 kilometers per hour. So why is this number important? Let's say I have a lesser fancy car where this number becomes 2. Okay, now with this number 2, the equations all remain the same. What changes are the numbers here and here. And if I just plot the response, it shows that it will take 12 seconds instead of 3 seconds earlier. So this number tau, the time constant, decides how fast my response is. And now we know a justification to this. At the higher the time constant, we had two time constant. Time constant of 2 took me 12 seconds, and time constant of 0.5 took me 3 seconds. At higher the time constant, slower the response, and vice versa. Lower the time constant, faster the response. And this is the mathematical explanation to that. Okay, so now I kind of know how signals respond to different signals, and it's also not just the property of the reference; it's also the property of the system itself in form of the time constant. Okay, so now I look at what is the natural response. Natural response, as we said earlier, is a response to a certain initial condition. Okay, I start with 5, I leave the system, it just goes back to 0. Forced response, the system starts from a 0 initial condition and reaches a steady state of 5. Okay, so we have, so you can just compute it mathematically. And what happens at, why is this time tau important? What happens at the time t equal to tau? Okay, what happens at time t equal to tau? I just take this number when t equal to tau. I'm just looking at the e power minus 1, and then I of t is at this value of t equal to tau just becomes 0.368 times the initial value. But this is in the natural response, like here. So in this is for the natural response. Okay. Similarly, in the force response, again with t equal to tau, I get to 60% of my steady state value. That is these numbers here and these numbers here respectively. Okay. So this number, the time constant in a first order system, is a measure of how quickly the system responds to changes. Mathematically, again, there is a standard form now for the first order system, like starting from here. 1 over tau s plus 1, and largely we are now interested in how the system, how different systems have different taus, and therefore how this tau therefore decides the system response of how fast or how slow. So this is defined as the time it takes for the system response to reach 63.2% of its final value for a step input, or decay to 36.8% of its initial value if it's a decaying system. This is just the natural response. And this is a force response where the force comes from as a unit step input. Okay. Now, in general, the time constant for a transfer in the time constant form, I can write any transfer function of in this way. Could have n poles and so on. Where k, I will have a system gain, and I will have a series of poles. For the first order systems, the time constant form takes this way. So I have a constant gain k, and in the denominator tau s plus 1, with the pole being at s equal to 1 over tau. Okay, so what we have understood so far is that smaller the time constant, faster is the response. And this is the general form for a first order system. If I have a system in this form, s equal to s plus p, I have a response of this form. H of t is e power minus pt times k, where p is the location of the pole. If p is greater than 0, s is less than 0, and the expression decays, right? What we saw in all our graphs. It is the RL circuit. Can draw it a little better. So this starts with some initial condition and eventually goes to 0. Okay. And if p is less than 0, pole is to the right of the origin. And in this case, my system response just goes exponentially. Okay, which means that if the impulse response is referred to as unstable, and now the time constant is just 1 over p, if p is the location of the pole. Okay, nice. So in general, now I have a standard form where I have a system gain k, I have a time constant, and this is how I can represent the first order system with the transfer function written in the time constant form. So I have y of s is the transfer function times r of s. I do all the inverse Laplace transform. I get a number like this. Okay. So this is the transient term, 1 over tau e power minus t. This is the transient term. And the steady state is 0 because I just look at how do I get the steady state. That is limit t going to infinity y of t. That is I'll just go limit t going to infinity e power minus t over tau with a 1 over tau. This goes to 0. I can also apply the final value theorem and check. So let's see how the final value theorem looks like. Y of s is k over tau s plus 1. The final value theorem says that y at steady state is limit of s going to 0, s times y of s. You can do the math. So this will be s k over tau s plus 1, and this becomes 0. Right? I think should be a easy exercise to check. Okay, the steady state is 0, and this is the transient term, 1 over tau e power minus t minus tau. Then I look at the step response. What if the input is a step? Then, okay, I do all the math, the Laplace, inverse Laplace, and I get something like this. So two things here I have. I have a k minus k e power minus t over tau. Okay. This is a transient term because it kind of dies down as at the steady state. This is the transient term, and this is the steady state term. I can also look at again y of t as limit t goes to infinity is again limit t going to infinity k 1 over e minus t by tau is simply k. Or I can also do it with the final value theorem. So in steady state, I have a value of k. So something over here. For different time constants, the plots would look like this. Again, we know what happens with lower time constants, higher time constants. They are kind of inversely related to the speed of the response of the system. Okay, so what if my input or the reference is a ramp? Ramp is a signal which is r of t is t for t greater than or equal to 0 and 0 otherwise. Right, so if you remember, it just has a form like this. This is my r of t with time. It's just a curve of increasing curve of slope 1. Okay, so I can just keep doing all the math and see what happens at the steady state is the signal will go unbounded at the steady state because maybe I'll just try to apply the final value theorem here. Y of s limit s going to 0, s times s, this is y at steady state is, so I have s over k s square tau s plus 1. So this will just go kind of unbounded, goes to infinity. Okay, and you can also see this in the time domain. The transient response still dies down. This will go to 0. Well, the steady state has something like this. K of t minus tau, it just keeps increasing, right? So this is with tau. Okay, so to summarize, we saw in this lecture the response of a first order system. We had the idea or had defined the notions of transient and steady state in addition to natural and forced response. And also saw how the speed of the response was depending on the time constants of the system. In the next lecture, we will talk about not just first order, but how systems respond to, say, for example, second order systems. And then we will generalize that to any nth order systems. That's coming up soon. Stay tuned. Thanks for listening.